Hi, my name is JAlfieri. I'm in EC 312, 332, and 342. And today I'll be talking about a transmission channel in a radio system through the different techniques and terms learned through each of the three classes. As shown here in this diagram, this is the simple view of a transmission channel. First, I'm going to give an overbase of kind of how an input signal passes through each part of the system to eventually be broadcasted out by the antenna to whatever receiver wants to receive the signal. So to first start with, you have the preamplifier. And basically this takes the low frequency signal that you have in the kilohertz and amplifies the voltage of it without any effect on the frequency of the signal itself. This is so that it can be passed into the mixer, which the mixer basically mixes two frequencies together. One is the input frequency, and then the other one is the local oscillator frequency set at by, say, for example, the cell phone that you're using. So 2.4 gigahertz for like Verizon would have this little bandwidth. So once the signal passes through the mixer, it again is amplified by the power amplifier. And basically what this does is it acts like the normal amplifier that you had before, but instead this has it so that this signal that's produced has power amplification, so it has enough power to actually travel through the air as it is sent through the signal. Because if it's not amplified in such a way to the signal having milliwatts energy, it'll dissipate after a few feet and is pointless for anyone else because no one can pick it up. So after you have amplification of the signal by the power amplifier, you have little noise within it that is unnecessary. In combination with a low and high pass filter, you can create a band pass filter so that a certain frequency range is only passed through and the rest of the noise is canceled out. So when the signal is sent, it is a clear, crisp signal that can be picked up by someone else. Finally, the signal flows through the duplexer, which either decides if the antenna is in the receiving orientation or sending orientation. In this case, we're talking about it being in the sending orientation. Now, to go into more specific details about each part, we're going to first start off with the antenna size. When a 2.4 gigahertz frequency is sent out, that is a very, very small signal size. And the reason you want to have those high frequencies is you're able to transfer more information as well as having a very small antenna size, since antenna size is in correlation with the wavelength. Also, it allows for transmission of multiple signals at once into one single frequency known as multiplexing. So going further in signal modulation, you have three types of signal modulation: AM, FM, and PM. Amplitude modulation is changing the amplitude of the signal itself, which, an example of that is a typical radio signal that you hear over an AM station. The other one is frequency modulation. Frequency modulation is basically, as it says, changing the frequency of the signal itself. The last one is phase modulation. This is not used as commonly. Mainly you can think of it as like the Doppler effect. So this is mainly used in radar waveforms to correct for the overcompensation of the Doppler effect depending how far you are from that signal that's being sent. Big difference between all these modulations is the power efficiency and the noise that is produced from each one. Specifically with AM and FM, AM, you'll notice a lot of times when you hear an AM signal on a station, it's very noisy. This is because of your environment. So you have a lightning bolt, all of a sudden that produces a very high electromagnetic or EM field that messes with your signal and actually attenuates it, and that's why you'll hear different noises and that noise happening. While with FM, it's not as noisy, so regardless if the amplitude changes of that signal, it does not change the frequency of it, so usually FM is a lot more clear and crisp. Signal modulation happens in the mixer itself. The main goal of the mixer is to amplify, condition, and filter the signal. How this is done is basically by an LC circuit. And what happens is this oscillation between the currents going back and forth, which stores the energy through electrical energy and then magnetic energy and back and forth and back and forth. In reality, there's a bit of resistance to the inductor depending on how big that wire is. So basically you have the baseband signal, that's that audio signal that you have, and then you have the local oscillator frequency. And how this is actually made is one single transistor. Yeah, that's it, one transistor. The transistor mixes the signal and amplifies it by that jam term at the same time. Basically, that IF, as you can see in the circuit here, that IF term is intermediate frequency, which is that kind of targeted bandwidth within that frequency that you're using. And the LC circuit is assumed an ideal inductor, so that you have that LC network that is the load itself. Why you have the load is because the load itself gives you the output mixture. Without the load, you wouldn't have an output. How do you actually combine the signals? In an ideal world, you use a transformer where the signals are stored within the magnetic fields and then combined into one. But in reality, you actually have very large capacitors that change back and forth, that switch very fast for the signal. When you want to actually get a very precise bandwidth within that frequency that you want, you have a transistor that has many capacitors, which one is chosen, so you can choose which little bandwidth you want within that frequency allocation that you have. So the bandpass filter basically allows the signal to flow through because it normally has noise introduced from electric and magnetic fields from the amplification of the mixer and the preamplification. And what the bandpass filter does is to remove that specific little noise by targeting one frequency range through bandwidth. If you want to increase that bandwidth of the filter, you can. And what's nice is you have fast response if you have a large bandwidth, but at the same time you also have a large bandwidth of signals flowing through, so not all the noise could be removed due to it. If you have a decreased bandwidth of the filter, that might be nice because only a little certain amount is passed through the filter, but it has a lot slower response time, so it's kind of the balance between it. And then again, the power amplifier allows the signal to be amplified enough to allow it to propagate through there without losing too much energy over time. And then the antenna just sends out the signal itself. So, thanks for watching.